Hello everyone and welcome to We Meet at EMC Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is System Efficient ESD Design for Robust Electronic Systems. Our speakers are David Pomeranke and Bernd Deutschmann. They will hold a presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask the questions via the chat function in the control panel. This presentation will be about 90 minutes long and the chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the presentation in the next few days. So now I will hand over to our first speaker, Bernd Deutschmann, and I wish you a good presentation.
Yeah, thank you very much. I also would like to welcome you all to our presentation. As already mentioned, the presentation is split in two parts. I'm here with my colleague David Pomeranke. And the first part is about protection against electrostatic discharges, and it's my pleasure to give you a short introduction into electrostatic discharges and especially the most important models that are currently available to test, for example, integrated circuits. So a short overview. I would like to talk about electrostatic discharges, as I said, as a short introduction, why this topic is important, and especially why this topic should be important to all of us, because we are all using electronic devices. And as you might already have experienced, there might be some electrostatic discharges happening when you are touching your smartphone, when you're connecting your smartphone to the power outlet, or when you're, for example, exiting your car. So there are many ways how electrostatic discharges can be generated. And in the end, there are also many ways how electronic systems can suffer from electrostatic discharges. But we will come to that in a second. Then I would like to give you a short overview about ESD models. For example, the human body model or the machine model or discharge device model. So these are all kind of models how we can check if electronic systems are robust and how robust they are against transient disturbances. And then we would like to talk a little bit more about protection structures. So how can we protect integrated circuits, for example, from transient disturbances? Yeah, some practical examples, some measurements and simulations. And this will be then especially the parts where my colleague David is then taking over. So a short introduction why this topic of electrostatic discharges is important. I would like to show you a short video clip. And you will see a kind of electrostatic discharge that luckily doesn't happen that often, but it can happen. So up to now, nothing special. So there is a woman at the gas station trying to fill up some gasoline. So there is nothing special so far. So now take a closer look what the woman is doing. So she's getting in the car, getting a little bit out of the car, lifting the feet, and then more or less jumping out of the car, ripping the pullover, and bang, there is an electrostatic discharge. So I think this woman has acted in a very, very good way. I'm not sure how I would have reacted if there is a kind of explosion in my car. So usually at this point, I'm asking students, what do we learn out of this? And the expected answers are, you have to be careful when you're touching your car, especially during winter times. There are very often electrostatic discharges because the humidity of the air is not that big. So these electrostatic discharges happen quite frequently, especially during winter times. And one answer to this question could also be that you should touch your car when you're exiting the car, so not jump out of the seat, don't rip your pullover. So be careful when you're getting off the car, because there could be some electrostatic discharges. Okay, so today we would like to talk a little bit more about electrostatic discharges in relation to microelectronics, and especially why we should be careful when we are touching integrated circuits, as you can see here on the screen, when a human person that could be charged up to a certain level is touching with the fingers an integrated circuit. Because then very often it could happen that there is a disbalance between the charges, and we can generate some electrostatic discharges from the human person into the microelectronic system. So when you're touching the pin of an IC, you might discharge into this pin, and then over the lead frame and the bond wire, this transient disturbance might travel into the integrated circuit, and there it can cause some effects, as you can see here on the screen. For example, really significant destructions within the microelectronic system. So among all transient disturbances, electrostatic discharge is still one of the most important reliability problems in the semiconductor industry. And I'm pretty sure the semiconductor industry has lost billions of dollars due to electrostatic discharge problems. And what you can see here on the screen is a typical damage that can happen when an electrostatic discharge is entering the IC. So for example, here on the left-hand side, you can see the bond pad. So this is this quadratic area here where the bond wire is usually connected. So here you can see the shade of the bond wire a little bit. And then usually there are electrostatic discharge protection structures around the bond pad, in this case, for example. And what you can see here is really a destruction of these electrostatic discharge protection structures on the chip due to too high electrostatic discharges. And here on the right-hand side, you can also see that metal traces were really destroyed. So here was a metal trace all over there. And also here you can see silicon really blasting out of the microchip due to the electrostatic discharge. So we should never overlook the damage that has been caused by this rebalancing of charges between objects when they are brought in close contact or when we are directly touching an integrated circuit. So where does this electrostatic charge come from? So there are many, many ways how electrostatic charges can be generated. A very important thing is triboelectric charging, mechanical contact and separation. So for example, if you're walking on a carpet, or as you've seen in this video, the lady was jumping out more or less off the seat of the car. So there is a kind of charge separation happening. So she was accumulating charge and then transporting this charge until she was touching the metal frame of the car, where she was then finally discharging. There is also ionic charging, direct charging. For example, if you're connecting the USB cable to your smartphone or to your PC, so the device that is connected to this USB cable can be charged up, and once you are approaching with the USB cable or with the connector, the socket, you might have a rebalancing of the charges between the objects, and then you can also cause electrostatic discharges. But there's also field-induced charging. For example, when the integrated circuit is brought into an electric field or moved along an electric field, as you will later see, for example, in this charge device model. So what are the typical models that we are currently using or have used in the past to simulate this kind of electrostatic discharges? For example, back in the 1960s, the first electrostatic discharge model was generated. And usually at this slide, I'm also asking my students, have you an idea when the first integrated circuit was brought onto the market, or who was the first one who were filing a patent for the integrated circuit, and when was it? As you can already see, it was somewhere in the time frame of the 1960s. So if you have some answers, you can also type it into the chat room. So who was the first person filing a patent for an integrated circuit, and when was it? Actually, it was in 1959, and the guy who was filing the first patent for the integrated circuit was Jack Kilby from Texas Instruments. Then a little bit later, more or less it is the same idea came up from Robert Noyce, who was working for Fairchild Semiconductors, which was then finally also the first company which was really mass producing integrated circuits. And this was all in the 1960s. And the interesting thing was quite a lot of integrated circuits that were produced during this time frame were somehow not fully functional. So they were produced, they were handled, they were shipped to the market, and then at the end, in the final product was not working properly. And then they made a lot of investigations, and finally they figured out that these integrated circuits were somehow damaged. They had a kind of pre-damage while they were shipped to the customer. And then after quite a lot of investigations, they figured out that this pre-damage might be caused by electrostatic discharges. Electrostatic discharges from human persons who were handling these integrated circuits. And then in the 1960s, the first ESD model was generated, the so-called HBM model. HBM in this case stands for Human Body Model, which is somehow simulating the electrostatic discharge that can happen when a charged human person is touching an integrated circuit, and thereby discharging into the microelectronic structures of these integrated circuits. So this was also the time frame where the first ESD protection structures were integrated. So the first I/O pins were equipped with diodes. There was one diode to ground and another diode to VDD in order to protect the I/O pins. And within the integrated circuit, especially within the power supply pins, there was also already some internal protection structure used. And nowadays we are using quite a lot of internal protection structures, so protection structures inside of the integrated circuit, and also external protection structures, as you will later see. And the very important thing is that the internal protection structure is matching also the external protection structure. So this should be, this is very important, because you can only protect your whole electronic system if you have a good internal and a good external protection structure, as we will later see. Okay, so the first investigations were done in order to figure out how can electrostatic discharges from human persons be avoided. And the first protection structures were also integrated into the ICs, but still ICs still got damaged. And people could not really explain why there is a damage, because there was not a damage from a human person, from a charged human person anymore. And finally, they figured out that also the machines that are used to handle the ICs, for example, the pick and place machinery, which is picking an IC and placing it onto the printed circuit board, also these machines could be charged up. And when the machine, the robotic arm, for example, is touching the integrated circuit, there might also be an electrostatic discharge from the machine directly into the integrated circuit. And during these days, the so-called MM, or machine model, was developed. But still, the HBM model and also the machine model could not explain all the problems that were happening to integrated circuits, because still integrated circuits got damaged. And finally, they figured out that also the IC itself could be charged up. So there could be some charge accumulation within the integrated circuit. And once the integrated circuit is touching somehow a grounded surface, for example, a metallic table, the charge that is accumulated inside of the IC can also be discharged out of the IC into the grounded table, for example. And in this time frame, also the so-called CDM model was developed, the charged device model. So this was then developed in the early 80s, late 80s, to explain this type of damage. So let me give you a short introduction into these three models that I've just mentioned. The first one, I think this is the simplest one, is the so-called HVM model. As I mentioned, it simulates a charged human person, which is discharging, by example, touching the integrated circuit pin with the finger. So it describes the procedure that occurs if a standing charged human person approaches a grounded IC. So the typical equivalent circuitry for the HVM model is just a capacitor, the CHVM, with about 100 picofarads. So this is the capacitance of a standardized human person. And this capacitance is charged up, as you can see here in this equivalent circuitry, by a high voltage source to a certain level. So in the old days, they used levels up to 8 kilovolts. Currently, we just have levels, 2 kilovolt is still quite high. So in an ESD protected area, where you have some ESD protection measures, usually the charging up of persons is not that critical anymore. So only a few hundred volts, or persons can, in an ESD protected area, only charge up to a few hundred volts, if at all. And then if this charged person is then touching with the finger the integrated circuit, there is this electrostatic discharge via this HVM resistor. So this is usually the resistance from the body over the arm to the finger and then into the integrated circuit. And the typical discharge resistance in this case is 1.5 kilo ohms. So there is then a discharge from the capacitor over the resistor into the device on a test, so into the integrated circuit. And the typical discharge waveform from the discharge current typically looks like this. So this is a simulation of a 2 kilovolt electrostatic discharge. You can see here a very sharp rising edge of the current, and then the current falls down by an exponential function due to the fact that we have an RC time constant from the capacitance and the discharge resistance, and also the input impedance in this case of the integrated circuit for sure plays also a role. So this is the typical discharge waveform based on this HVM model for the IC level testing. So next there is the model for the machine model. This is not used that often anymore. The basic principle is the same. So we have a capacitor. The typical capacitance of such a machine is 200 picofarad. At least it was standardized with 200 picofarads. This capacitor is also charged up by this high voltage source to a certain value. So this AEC Q100 standard defines levels from 100 volt to 800 volt. So usually test levels are 200 volt, for example. And then this capacitor is more or less directly discharged into the IC, into the device on a test. And then the discharge current looks very often like this. So there is a kind of oscillation which is built by the parasitic inductances that are also available in this discharge current loop, and especially by the impedance that is seen when you're looking into the IC, so into the discharge port from the terminal 1 to terminal 2 of the integrated circuit. So very often we have a kind of oscillation of this electrostatic discharge current. And the last model that I would like to explain is the so-called charged device model. As I already said, so charge can be accumulated within the integrated circuit. And once the IC is approaching, for example, a metallic table, for example, there can be some discharge from the IC pin into this grounded table, for example. And how much charge can be accumulated within the IC is a little bit complicated to say, because it really depends on the IC itself. So is it a big package? Is there quite a lot of metal structures within the IC? So it's not that easy also to model such a kind of charge device, because it's not that easy to model how much charge is accumulated within the integrated circuit. The procedure how this IC is tested is usually done like this. So we have the IC, the device on a desk, placed on a charge plate. So for example, the pins of the IC are facing upwards. And then we can charge one of the pins by a high voltage source by closing the switch S1. And we're opening the switch S1, so there is some charge accumulated within the device on a desk. And then we can close the switch S2 to discharge on another pin this device on a desk here in this loop here. The typical discharge waveform looks like this. So there's also a kind of oscillation, which also depends on the parasitic impedances that are in this discharge current path, and also the charge that is accumulated in the device on the test. So usually we have very high TI over dt, so the current is rising up very fast to pretty high levels. For example, in this case, for a 500 volt ESD CDM model, the current goes up to about 10 amps, for example. Okay, so all the models that I've talked about so far are so-called IC level models. So they are used to test integrated circuits, and in this case, they are really used to test very often only the unpowered IC. So the IC, which is not fully operative, where there is no power supply, it's just a kind of packaging and handling test, defining will the IC survive the touching of a human person, will it survive when it's shipped in a shipping tube, will it survive when a mechanical system is taking the IC and placing it somewhere on the printed circuit board. And this is very important because we are only testing the unpowered IC, in this case only for destructive tests. So checking if the IC will survive the test, not checking if the IC has any kind of malfunction, because the IC is not powered in this case. At the system level, when we are testing then finally the whole electronic system, the situation is completely different. Here very often we have the IC used in an electronic system, so there are also quite a lot of external components, decoupling capacitors, for example, and the IC is really fully powered up and fully operative. And in this case, we also have to test regarding the robustness of the whole electronic system against electrostatic discharges. And in this case, we are also using an HBM model. And very often we are using an ESD gun to check how robust is a whole electronic system against electrostatic discharges. There are different standards, and an important one from the automotive area is according to the ISO, International Standardization Organization, 10606, which is defining also this human person model for electrostatic discharges when a human person is touching an electronic system within the car. And here on the picture, you can see different discharge waveforms. And if you compare these waveforms to the HBM waveform on the IC level that I've shown you before, you can see significant differences in the discharge waveforms. For example, here in this HBM model for the system level test, you can see a first rising sharp edge of the current. So the current is rising pretty fast. And then afterwards, you can see this typical electrostatic discharge that you might have seen before in this HBM model for the IC level. So the question is, where does this first discharge come from? Actually, it's somehow simulating a charged human person that is, for example, handling a metallic tool, for example, a screwdriver. So if the person is charged up to, let's say, 2000 volts, also this screwdriver that is held in the hand by the person is charged up to this voltage. And when the person is touching with the screwdriver, for example, the connector, which is connecting the electronic system, and the connector, for example, has a direct cable or printed circuit board to the IC pin, then we might generate an electrostatic discharge from the charged human person into the cable, into the connector, or in the connector into the cable, and then into the integrated circuit. And the first discharge that you can see, this first spike here, raises more from the fact that there is a discharge from the metallic tool, from one metallic surface to the other metallic surface of the connector. So there is not that much discharge resistance. And then later on, the discharge from the charged human person, so from this capacitor that is provided by the person itself, will then be discharged by the resistance of the skin and of the human body and of the arm. So the first discharge is mainly the discharge of the stray capacitance of this metallic tool, and the second discharge is then the real discharge of the charged human person. And in the standard, there are different RC time constants depending on how the test should be done. So for example, there is a 350 picofarad capacitor or a 150 picofarad capacitor. And also the discharge resistances can vary between 2000 ohms and 330 ohms. And this really depends on what kind of simulation model is used. For example, for the resistances, 2000 ohm simulate the discharge of a human person that's without any metallic tools or directly through the skin. And 330 ohm simulates the discharge of a human body or a human person through a metallic part, for example, this screwdriver that I've mentioned before. And then also the capacitor varies because it depends if the person that is charged up is within the vehicle, so within the car, or approaching some electronic systems from outside of the vehicle. Typically, discharge levels might range up for the contact discharge up to 20 kilovolts, or for the air discharge, sometimes also up to 25 kilovolts. And depending on what car manufacturer and what OEM you are providing with integrated circuits, they have different ranges or test levels that should be used in order to characterize the electronic systems. So here on this slide, you can see the typical differences between the system level and the IC level HBM test. So both tests are simulating the charged human person discharging into an electronic system. On the IC level, directly discharging into an integrated circuit, and on the system level, very often discharging into a whole electronic system, not just one integrated circuit, for example. And this is the simulation of the discharge current for a 2 kilovolt ESD discharge. So both currents are provided by a 2 kilovolt charging voltage. And you can see a significant difference between the system level and the IC level test. So at the system level, the current rises up very fast, in this case up to 8 amps, while in the IC level, the current goes up to 1.4 amps, for example. And on the IC level, you can see the discharge current looks like this. And on the system level, you can see the two tips that I've tried to explain before. And the most important difference is really the way how the test is done. On the IC level, we are usually testing the IC unpowered, not fully operative, and we are testing the IC just if it survives the test, if there is a destruction or not. And at the system level, we are testing the whole electronic system, not just for destruction, but also for any kind of malfunction. For example, if the system gets a reset or if it's working properly within a certain tolerance range. So very often for the development of electronic systems, it's very important to pre-estimate if your electronic system will survive this ESD testing or not. And therefore, we are using very often simulation tools. For example, here you can see a very nice model that was developed also by David, who is giving the next talk, in order to simulate the discharge current of this ESD gun for the system level test. For example, this is a very simple equivalent circuitry here on the left-hand side. You can see capacitors, resistors, stray capacitances, stray inductances. There is also the switch that can be closed in order to discharge an electrostatic current into an IC under test. And here in this paper, there is a very good description on how to model an ESD gun. And in the table, you can also find all the values for the resistances and capacitances that you can use in order to make your own simulation model for this ESD gun. So we also did it in our lab. So this is our LTSpice representation of this model. And here on the right-hand side, you can also see the typical discharge waveform, as I mentioned before, that is standardized in this automotive standard, for example. And this can also be used then, as I said, to pre-estimate if your electronic system will survive this ESD tests or if there will be a kind of malfunction within your system. Okay, now the question is, how can we protect our electronic system from this kind of electrostatic discharges? And there are many, many ways how to protect integrated circuits or whole electronic systems. So maybe we can split these protection elements into overvoltage protection elements and overcurrent protection elements. So typical representatives of overvoltage protection elements are transient voltage suppressing diodes. So for example, this one here. Also, there is a TBS diode array, or they can also be found in this kind of package. There are so-called gas discharge tubes. Usually they are not that good for small electrostatic discharges, as I've explained before, this ABM, HBM models, for example, but they are very often used, for example, for big electrostatic discharges, like protecting against lightning strikes. And there is a big variety of so-called varistors. So for example, these ones are provided also by Würth Elektronik in this package, and there are also varistors in an SMT package, for example. And usually these transient voltage suppressing elements are placed in parallel to your device on a test. So if there is a kind of electrostatic discharge, then these protection elements provide a low impedance bar, very often down to ground, to divert the electrostatic discharge to ground before it can enter the integrated circuit, for example. Then here on the right-hand side, you can see the overcurrent protection structures, like thermistors, so positive temperature coefficient elements, fuses that are blowing if the current is too big, or also resistors can be used. And later on, we will see how good or how bad are these elements when it's about protecting, for example, integrated circuits. So let me switch to the next slide, and there I would like to give you a very short overview of some important protection elements. For example, this transient voltage suppression elements, the TBS diodes, for example. There are unidirectional or bidirectional protection elements. So this is the typical symbol that is used. And you can see in the forward direction, the protection element very often acts like a standard diode. And in the reverse current or in the reverse area, there is very often a voltage breakdown. For example, here, where the element then starts to conduct and to divert the current, for example, to ground. So very often they have a fast response time. So in the nanoseconds, they do not wear out, so they can be used hundreds of times as long as the current is not that big. They might have some leakage current. This is a drawback. You can already see if the voltage is not that big. There is also some current flowing in the reverse direction. But they are very often used to protect electronic systems or integrated circuits. So the next one that I've already mentioned is the gas discharge tube. Usually there are two electrodes separated, and in between there is a vacuumed inert gas, and then if the voltage between the two metal plates or between the two electrodes is raising up a certain level, then there is a discharge within the inert gas, and then the current can be discharged directly between the two contacts. They provide low capacitance. This really depends on how these systems are built. So what is the distance? How big are these metal contacts? So yeah, the capacitance might not be that low, depending on the gas discharge protection system that is used. They have a very high surge capability, so they can really discharge quite a lot of electric energy, as I mentioned, for lightning strike protection. But the problem is the response time is not that stable, so it takes a long time until it's really triggering, so therefore it's not a very good protection element for this HBM ESD protection, so directly protecting integrated circuits from this electrostatic discharge from human persons. Yeah. Another very often used ESD protection structure is the varistor, or the voltage-dependent resistor. They provide a very fast response time, low standby power, and they are produced in different ways, different sizes, and depending on how many so-called microvaristors are then connected in series or connected in parallel, the manufacturers can define the voltage, the breakdown voltage when this varistor starts to be active, and also what kind of internal resistance this varistor then finally will have. And there are many, many different types of varistors that are currently on the market. And I'm pretty sure there are many, many more protection systems that should be mentioned. But in order to give you a short demonstration on important protection systems, we got a very nice demonstration kit, also from Würth Elektronik, that we are usually providing to our students to really have a kind of look and feel experience to figure out what kind of protection structure is very efficient and how does an electrostatic discharge feel if we are using the right or the wrong protection system. So the way how this system is working, so we have an discharge area, so for example here, and there we are shooting an electrostatic discharge into this area, and the student can then place the finger, the thumb for example, between this metal area here and this metal ring over there, and then he or she can really feel the electrostatic discharge. So the first place here is more or less a reference, so there is no electrostatic discharge, so you can really feel an electrostatic discharge from a piezo lightener. And then we have different protection systems. For example, here, number one is a simple resistor. In this case, it's a 1 kilo ohm resistor directly in the line, so a series element. The next, number two, is a transient voltage suppressing array. So there are TBS diodes within this array. This is in parallel to the protection system, or to the system that should be protected. So it's once it's triggered, it's diverting the ESD current to ground. So here is the ground connection point. Number three is a chip varistor, also connecting to ground, so protecting the electronic system by diverting the current before it can enter the integrated circuit, or in this case, enter the finger of the student. Number four is a chip beat ferrite. So ferrite is more or less the same thing as a resistor, but it's frequency dependent. And here the ferrite is selected to be or to provide a high impedance at very high frequencies. As you've seen, the discharge current waveform has a very sharp rising edge, so there are a lot of high frequency contents within the ESD discharge. So therefore, maybe also a ferrite, which is providing a high impedance in a high frequency range, might act as an ESD protection. And number 5 is an LC circuitry. So it's an inductor here in series and a capacitor then diverting the current to ground. And then we are asking usually the student, what do they think? What kind of protection structure is the best? Is it number 1, here the resistor? Is it number 2, the TBS diode array? Number 3, the chip varistor? Number 4, the ferrite? Or number 5, the LC circuitry? And if you're interested, you can also participate to this. Unfortunately, we do not have this look and feel experience here in the live seminar. Usually we are asking then participants or volunteers who would like to press their fingers onto these protection structures in order to figure out what kind of protection structure is the best one. Unfortunately, in a live webinar, we cannot do this. But you can also participate in a survey. For example, this is pretty simple. You can type in this URL into your smartphone or into your tablet PC. So it's www.fbr, stands for feedbacker.io/ESD. Give me a second, then I can start the survey. And if you want, then please participate to this quiz. So number 1 is the resistor. Number 2, you can vote for the TBS diode. Number 3, you can vote for the chip varistor. Number 4 for the chip beat ferrite. And number 5 was this LC low pass filter circuitry. So we already got over 70 participants. So thank you very much. We'll keep the survey open for a couple of seconds. Okay. 5, 4, 3, 2, 1. Okay, and last chance. Okay, and then let's check the results. So I have to switch to another screen. So if everything works out well, then you should be able to see the outcome of the survey. So the clear winner in this game is the TBS diode array. Then it's very close. We have the chip varistor on number 2 and number 5, the LC low pass filter. And believe me, this is absolutely correct. So usually now we are making the look and feel experience. So a volunteer can now press the finger onto these different protection structures, and depending on the reaction of the participant, you can then really see how good or how bad is the ESD protection. And yeah, as you already have figured out, the resistor is not that effective as an ESD protection structure. Why? If we are doing this experiment, we are also asking the students to take a very close look while we are shooting the ESD disturbance into this resistor. And you can really see a spark jumping from one terminal of the resistor to the other terminal, also bypassing the resistor, and in this case, not really protecting the human person, or in this case, the integrated circuit. If the student is pressing the finger at number 2 at the TBS diode, usually they do not feel anything. So this TBS diode is really a very, very good protection structure. Same goes for the varistor and also for the low pass filter. And on the chip beat ferrite, the students sometimes really feel the electrostatic discharge still in their fingers, because in the same way as the resistor, a chip beat ferrite is in this case not that effective to protect human persons or integrated circuits in this case. So very good, so we're absolutely right. the TBS diode in this case is really the best protection structure that can be found here on this very nice demonstration board that we got from Würth Electronics. Okay, and at this part, I would like to hand over to my colleague David, who will give you some further information onto the so-called seed approach, how to really figure out how we can protect our electronic systems.
One was two questions which David already answered, but I think it's good that you answered also to all of them. There was on the varistor, you wrote down that the varistor capacitance is noted as pro and negative. What now?
Okay, let me just check the question. So the varistor, go back to the slides. Yeah, as I tried to mention, the varistor really depends on what size does the varistor have. And there are quite big ones, and they can then provide a big capacitance, but there are also very small ones, and they have small capacitances. So in the end, it really depends on what kind of system you would like to protect and up to which level you would like to protect your system. So does a very small varistor provide a good protection, then the capacitance is usually very small due to the size of the varistor. But do you need quite a lot of protection? Then you need a big varistor, and then maybe this capacitance that is provided between the two terminals of the varistor is too big. I'm not sure if this is really answering this question.
Good. Thanks.
Okay. Okay, this is David Pomeranki. I hope I'm unmuted. Is that true?
Yes, we can hear you.
Okay, then let me start. Yeah, it's an honor to have such a large audience in such a talk. And I'm going to talk about, let's say, I call it the future of ESD protection. So my focus is on, how to protect high-speed I/O. I mean, high-speed like USB 3.1, 3.2, 4.0, or any in the interfaces which have high data rate, and they go into ICs which are made from really small structures like 7 nanometer, 5 nanometer, 10 nanometer. So basically, high-speed I/O in modern ICs. How to produce ESD protection. And of course, if the speed is high, we cannot put a large capacitance there. So 1 picofarad is probably way too much. We talk about ESD protection structures in the external TBS diodes, which are below 1 pico, like 0.5, 0.1 pico, or even lower devices exist. Now, why do we need to do this? In this diagram, I show what happens here in my mouse. 1 second, I need to change something. Okay, in this diagram, I show ESD current and voltage. And the normal operating area of an IC may be 500 millivolt swing, maybe 5 milliamps for the data. And if we go to high-end current, maybe 2 amps for 100 nanoseconds, then the IC is destroyed. If VT2 is reached, the voltage is too high, the current is too high, we get thermal damage. So we are limited by current. Now we're also limited by voltage, because if the voltage is too high, even for 1 nanosecond, there may be charge carriers placed into the gate oxide, and the gate oxide gets damaged or destroyed. Now, when we go from 10 nanometer to 5 nanometer or smaller, then the cost per wafer area, so the cost per 1 square millimeter of wafer goes up. But the integration density goes up faster. So the race is won. It makes sense to make structures smaller, digital structures. But ESD protection is differently. It's current driven. And there are current limits. For example, there's a certain current density which can flow on the silicon oxide, on the silicon. And the current density doesn't change with scaling, so you cannot make the ESD protection structure smaller. The other is the metallization. The metallization gets thinner and smaller which is fine for the digital signal, but it's not fine for ESD. You need many contacts and a lot of area and metallization now to carry the current. The consequence would be that the cost per IC, which is put into ESD protection, will go up the smaller the structures are on the IC. Now, why is ESD protection in general needed? Most ESD protection is for manufacturing and handling. In manufacturing and handling, one can do a lot of ionizers, conductive materials, etc. One can control the voltages very well. Now, on system level, it's differently. On system level, there's no control. And the IC protection structures in the IC, which are meant for CDM and HBM, they also help in system level, but they're not a good predictor, as Bernd says. But we are forced now for the high-speed IOs, because the ICs are much more easy to be damaged by system-level ESD. We are forced to put some protection on the board, so on the differential lines of USB. And so this normally one would have done this by datasheet, but right now the protection window in voltage may only be 3 volt, and the protection window in current may only be, we have to limit below 1 or 2 amps. So we are forced to go more to a simulation-based methodology for ESD protection instead of a datasheet-based protection. Now, let me look, I will advance through here a little bit faster. Let me look at, this is an example where there's an ESD entering a board. This is a board. There are some trays. The trays has maybe some inductance, resistance. Then there's some inductance inside the IC. Here's the IC. And there's an ESD protection here. And there's just shown if too much current flows, it gets damaged. Now, let me add an external ESD protection here. Now we have a TVS here. And if well designed, the ESD protection will take the current, and a little current flows in the IC. Now, this is can be a race condition, because in some, if the external IC is TVS is badly selected, then the internal protection will actually protect the TVS. It's not a good idea. So in the end, we have to protect against 2 things. Number 1 is we have to have not too much current flowing into the IC. Most of the current has to be on the TVS, and we have to make sure that even for a very small moment, like a few nanoseconds, 1 nanosecond, we don't get too much voltage at the IC, and it would cause gate oxide damage. Now, this is shown for positive voltage. It's also true for negative voltage. Now, in the design, it's really critical that we clamp the voltage very close to the signal voltages, and we have to make sure that the turn-on race, that the external turns on faster than the internal. If the internal turns on and the external tries to turn on much later, then there's no voltage for it to turn on anymore, and the IC will be destroyed. Now, let's look at some modeling. So the consequence is we need to model the TVS, and we need to model it in many regards. And we also need models for the IC. This is a much more difficult problem sometimes to get, but some manufacturers provide ESD relevant models for their critical IC IO pins like USB, etc. Now, the TVS models, they need to model, one thing is the small signal behavior. So basically, if the TVS destroys the signal integrity, if the TVS destroys the I diagram because capacitance is too high or its resonance is at a bad location in frequency, then the TVS is not useful. So the small signal model needs to be done, and the large signal model. Large signal model is like the protection model. Next is, it has to be a transient model. So basically, the turn-on behavior has to be modeled. And there's multiple aspects which influence turn-on, like inductive effects, snapback delay, conductivity modulation. A couple of items cause a voltage overshoot at the beginning of a pulse due to the TVS. Then models need to run on multiple SPICE platforms. We cannot just force everybody to use like ADS, or it's better if they're written in basic Berkeley SPICE, and then they can run on every model, on every solver. Now, in most cases, we don't know what's in the TVS, so it has to just be done by measurement. There are just 2 measurements needed: VNA, vector network analyzer, and very fast TLP. And models need to be useful for snapback devices, varistors, spark gaps. So the model frame has to be stable over the devices. Of course, parameters need to be adapted. And it's good if models are accepted. So multiple people work on models, and every model has its advantage and disadvantage. And it's good that these models are promoted, and then people learn how to use them. And of course, the models get improved. Now, this is all driven by the Industrial Council on ESD target level, a rather important organization in ESD standardization on ICs, maybe not standardization, but setting industry standards, industry best practices, about 50 to 100 companies in it. And of course, every model needs to be expandable if new effects are discovered, which are relevant. Let's look at some of the TBS devices. Bernd already did this a little bit. Now, the left here is a snapback device. And snapback devices come basically in two classes. Here is the current, here's the voltage. There's snapback. This is a shallow snapback device. And then the voltage goes up over current. And we have a slope resistance here. The slope resistance is often like half an ohm, 0.1 ohm, very low values, maybe half an ohm is already maybe a higher value. This is a shallow snapback because it snapbacks only little. But there are devices which snap back like from 7 volt to 1 volt. And then they have here snap resistance. Why do we want deep snapback devices? The reason is if we have low capacitance requirements, the area inside the TVS has to be small because the capacitance goes proportional to area. The problem is if the area is small and we have to dissipate a lot of energy, it will die. But the energy is, of course, the integral of the power, and power is V times I. So if we can reduce V, the voltage across the TVS, then much less power is dissipated inside the TVS. So we can make it smaller for the same capacitance, and we protect the IC much better. So many of these devices are deep snapback devices. There are also non-snapback devices shown here. They look a little bit like a Zener diode. They're not really Zener diodes because a Zener diode would have way too much capacitance. But you can put a pin diode in series with a Zener diode, and then the capacitance is low. Now let's look at other devices, spark gaps. Bernd said that spark gaps, their voltage goes up. Now in this case, 650 volt. Then it snaps back, and then the voltage of all snapback devices like 25 to 40 volts. But Bernd said the turn-on time is way too long. There are some fast turn-on devices. They're nonlinear polymers. They're sold by Würth, Elektronik, and a couple of others. They have very low capacitance, like 50 femto. But they take a couple hundred volt to snap back, and they turn on very fast, sub-nanosecond. But they still have a burn voltage of 25 to 40 volt, which is simply too much to protect most IC. Another class is of varistas, which is shown here. Very shallow, very soft curves. The problem is for high speed where you need less than a pico, varistas are not useful because they will be so soft, their curve, they won't protect anymore. Varistas are really good against surge because they have volume. They dissipate the energy in the volume, which is good. So they can handle joules, many joules, but they're completely useless for very high speed IO protection. Now this is an illustration of an IV curve, voltage, current. And this is the illustration of the model. And the model has like a small single model, that's single integrity. And all of the rest thing is the large single model. There's some current before snapback. SB is snapback. FE is falling edge of the voltage. CM is a common conductivity modulation, a change of over time, a change of the conductivity over time. And then comes the main IV curve. So if we go in, here's the linear region, maybe up to a couple volt, nothing happens. Just the capacitance dominates the effect on single integrity. Then for snapback devices, some current may start to flow. This current is needed to initiate the snapback. Then snapbacks happens. And then we go into the region where all the other models work together. And then if it gets the current gets high for a long time, the device gets hot internally, and then the resistance goes up of the device, which is normal. Hot, for example, resistance goes up, the same for silicon. So this is a general illustration on how it's reflected inside the models. Now this is time domain. Now the same thing in time domain. This is voltage, time. A pulse, if there's no big voltage, only the green region, the capacitance is relevant. Now the voltage goes up, an overshoot happens, then the device snap back, and then the voltage drops in like 1-2 nanosecond, this falling edge, and then it drops further. It may take another 10 nanoseconds until it reaches the quasi-static range. This is the main IV model, and this pink one is kind of the slower drop, and the falling edge is the faster drop. Each is modeled by a couple of SPICE elements. I will not go into the details of the SPICE model because it would take too long for the seminar. Now, the model sort of consists of small signal model, snapback, and then, the main IV curve. If we go a little bit onto the topology of the model, the anode is here, the cathode is here. So first is an LC model, L and a couple of resistors for small signal. And then if the pulse is positive, it goes via this diode. This is an ideal diode, perfect diode, better than you can buy. SPICE can do it. And then there's a diode, a modified diode. This is not a 0.7 volt diode. This is a modified exponential function diode to model the sum of the currents. Then we have a snapback delay model, conductivity modulation. At D3 is the main IV curve. Again, it's a modified diode model. It's not an 0.7 volt diode. This can be the Zener diode, can be many other things. This is for positive, and here's for negative. We'll just look at one of the blocks now. 2 blocks, sorry. The small signal model has the junction capacitance here and the apparent inductance. And I really want to point out this is the apparent inductance, because everybody says, oh, this capacitor has a equivalent series inductance, ESL, and it has like 2 nanohenry, or we say 1 centimeter of wire has 5 nanohenry of inductance. Mathematically, that's completely wrong. You cannot assign inductance to anything where you don't know the complete current path. So a short piece of wire cannot have an inductance. Same with a capacitor. But we always solder these capacitors in the same way on the PCBs. So the practical loops formed on most PCBs are similar. Then we can say the loop has this inductance, and we associate some part of the inductance to the capacitor. So this is not an inductance of the capacitor, that's an apparent inductance or efficient inductance. But we should be always reminded that this is not, that you cannot assign inductance to a single component. Only if you know the complete current path. Now there's a junction capacitance here. I told you that's from maybe 0.1 to, of course, high values, but for high-speed design, usually just 0.1, 0.2, 0.3 picofarad. Let's look at the quasi-static IV model here. And in the plot, it's current here, voltage here, negative branch, positive branch. And on the positive branch, we see in the measurement the voltage overshoots and snapback. This is deep snapback. It snaps back from 18 to 2 volt. And if we just take the IV curve model, so not the complete model, we see the simulation doesn't capture the overshoot, but it captures the slope here, the slope resistance. And here we see for some diode, we see the modified SPICE parameters. You know, in SPICE, a diode is modeled by the saturation current, by the series resistance, and by a, let's call it an efficiency coefficient. By just modifying this, one can basically match the curves. Of course, in the end, we have to add the overshoot model to it. Now look at a little bit more in detail in an IV curve current, voltage. This is from a TBS diode. We see the thing is not just one slope, but has 2 slopes. So there's an overshoot, 1 slope, 2 slopes. Now to get 2 slopes, we just put 2 diodes in parallel, modify the parameters here, modify the parameters here, and we see the red curve is, I think, the modeling. It matches not badly to the device. Now let's look at snapback. In snapback, the following is assumed. This what's shown is the voltage at the device and time. So we are time domain. Let's say we apply 30 volt TLP. Actually, 30 volt is not a lot, but let's say we apply 30 volt TLP. The voltage overshoots, and then snapback happens and comes down. And here's VT1. VT1 is the snapback voltage. So here, at this moment, it goes over snapback. And what we do is we integrate the area of the voltage above snapback voltage to the actual voltage. We integrate that, And if this area reaches a value, we say snapback. Here the same S2, this time 22 volt TLP, much less. So we don't go at high, but it takes longer. So S2 and S1 should be the same. Actually, it doesn't look like it in this diagram. Now, in this case, S3 wasn't enough. There was simply no snapback. The pulse just ended. This is how, for example, snapback is modeled. Now, we modeled a bunch of devices. Here, Nexperia, Toshiba, Semtech, but also spark gaps, varistas, and many Würth devices will follow soon. Many models. I think we work on 70 models for different Würth devices using this modeling scheme, and I think there'll be first wave will be in LTSpice, announced in LTSpice. They can be converted to BerkeleySpice. Then LTSpice and BerkeleySpice are rather similar. Now let's look at how they perform. This is, for example, a snapback type TBS, voltage current. And we see the IV curve is not badly modeled here, and the slope resistance is really low. This is and overshoot to 9 volt, a deep snapback device. Now let's look in time domain. This is 30 volt TLP, still not a lot. And we see 10 volt is reached for some time until something happens. That's snapback delay. And then it goes down and somehow reaches its final value. The pulse is, by the way, short. The test pulse was really short here. Or we take 100 volt TLP. We overshoot now to 20 volt and go down, and at that the pulse is just 5 nanoseconds long. So the model is, I don't say perfect, but it's some reasonable match, and the match is usually always try to achieve over a broad range of voltages and rise times. So ESD may be fast rising 100 pico, but if I touch with my finger, it's slow rising, maybe 10 nano. So especially for the slow rise time, often the problem happens that the IC protects the TVS. The voltage at the TVS never reaches high enough for snapback, for slow rising, because the ESD protection inside the IC clamps the voltage. So the modeling for slow rising ESD is often a much more difficult case than for fast. Take another device, a spark gap. Bernd said, they take too long to turn on. Look at this voltage time. So we're in time domain, and we apply 800 volt to it, quite a bit. Takes, what's that, 20 nanoseconds to break down. If we apply 1000 volt, it takes, 10 nanoseconds to break down. And at 1200 still takes 5 nanoseconds to break down. That's way too much. No IC easily would survive that. Usually spark gaps are useless for ESD protection. There are some exceptions, very good, but in most cases not. Take a varistor. I told you they are very soft. Voltage, current, we see 25 volt, then something happens, and at 50 volt we got 15 amps. And for example, at this point, if we go to this diagram, we see an overshoot to 100 volt, and then we see it takes some time to reach the final value. This conductivity modulation, that's basically where the conductivity inside this device is still changing, has different reasons for a varistor than for a silicon device, but all of these devices take some time to distribute all the charge carriers such that the final value is reached. And we see here for 100 volt, we see the varistor takes maybe 20 nanoseconds before it kind of reaches a static value, but the values are too high anyway. Now let me see how much time we have. Oh, we are pretty good. The TBS models, the ones here done, they have small signal model. They model the quasi-static curve, and then all the turn-on effects, which is snapback delay, conductivity modulation, etc. They're all modeled in SPICE model, and the modeling frame can be used for snapback, deep snapback, varistor, spark gap. The parameters, of course, needs to be adopted based on the measurements. Now let's use a model. Let's take a usage example. Now this is the structure we have. Let's say here's an IC, and every IC has an ESD protection. And let's say this IC has a dual diode protection. Has a big capacitor on the outside, 200 nano. It's like a short for ESD. And here we just have some decoupler and get some power. The signal comes here, and we, in this model, and actually also in reality, we can measure the voltage here directly at the IC. Let's say 1 millimeter from the IC, we measure the voltage with, let's say, 2-3 gigahertz bandwidth. And we can measure the current. We measure the current inductively also directly at the IC. So we know the current which flows into the IC. We know the voltage very close to the IC. There's a trace, 0.5 nanosecond. It's about 5 centimeter. And there's a DC block capacitor. You know, USB has DC block capacitors. Here's our TBS diode. In our model, it's a snapback model. And here's an ESD source. That can be an ESD generator, TLP, or human skin discharge, a different type of model. Now, let's look at an example. This is an example of the same circuit. This is the voltage at the I/O pin. So that's actually the voltage pretty much directly at the IC. And simulation and measurement. And what do we see here? First, nothing, and then back, overshoot, and then ringing, and then it stabilizes, and then the pulse is over. And let's zoom into the front section. We see nothing, then an overshoot, a little bit higher in the measurement and simulation. And you see the ringing, and the ringing calms down. Why is it ringing? Well, think about the following thing. We have a trace, 0.5 nanosecond long, and on one end is the IC, the dual diode protection, and it turns on. So it's really low impedance. On the other side, we have the TVS, it turns on, really low impedance. So we have the trace left and right pretty much shorted, so it rings. It's a transmission line, left, right, shorted. It rings at the natural frequency of the transmission line, and the transmission line is 0.5 nano. So the natural resonance is at 1 nano, 1 gigahertz. That's the ringing we see here. And then there's losses in the trace and the diode. So the ringing kind of stops because the energy, the ringing energy has been dissipated. Then it reaches a static value, 2 volt at the pin. That's quite an acceptable value for the current will be relatively low. Let's look at the current. This is the current flowing into the pin here. And we see the jumping up, ringing, then it goes up, then it goes down again. So look at the zoom. At the beginning, the current rings. Of course, it's the same as the voltage, same phenomena, transmission line, both sides, very low impedance. It rings at the natural frequency. But then it goes up. Why does it go up? Well, think about the following thing. The traces transmission line at higher frequencies, at lower frequencies, we look more as an inductor. And inductors don't like current change. So the inductance of the line, of this transmission line, basically forces against the current change, and slowly it can rise. And then goes down. Wow, it's got even more strange. You know what happens? This 100 nanofarad capacitor charges up. For example, if it charged up to 1 volt, then there's 1 volt more at the TVS. And that means more current can flow through the TVS. So the more the capacitor charges up, the more the balance shifts to the TVS, even if it's 100 nano. What I wanted to show is in this simple model, there's so much things going on, resonances, ringing, inductance, capacitance, charging up, that without simulation, one could have never guessed it. This type of problems can only be solved by simulation. There is no intuitive solution without knowing actual data. How do we get the data? Let's look at that. How do we get these data? We have a modular system, I call that Lego, and that allows us to put ICs on, current measurement, ESD generator, TLP, etc. Because we learned if we take a big evaluation board and we solder 10 times and we blow up an IC and take it out and put a new one in, blow it up again in testing, the board is dead after some time. And we cannot measure directly at the IC well, especially current. So we need a more flexible system so we can measure where we want. And if some IC dies, we only change a small part. This is done in a system like that. This is a base plate, many holes, all have threaded. And we have many modules here, just 3 modules shown, no 4. SMA launch, about 15 gigahertz bandwidth. Voltage measurement probe, a couple gigahertz bandwidth, let's say 4 or 5, via 1 kilo ohm. Here's a current measurement. You know, as you see 2 traces parallel. They are inductively coupled. And via some passive integration and some mathematics, we can reconstruct the current. And they have about 60 or something modules. We have source modules like SMA input. First one can SMA input there, do a network analyzer measurement, characterize the system, and then change to USB and put a USB cable in and see what happens then. Then we have different TBS devices, voltage pickup, rise time filters, attenuators, traces, and we have two sources. I'm going to see the sources soon. This is just to show that the system works relatively well at RF. This is a 45-degree launch, 100 millimeter trace, 45-degree launch. This is impedance. This is TDR, time domain reflectometer. So first we have 50, then there's a little bit imperfection at the connector, little bit imperfection at the transition board to board. The trace is not really 50 ohm, but not too far away. And then the same on the other side. Impedance profile is good. It's about 15 gigahertz bandwidth. Now, this is the current measurement. Current measurement is done inductively. And inductive means the IDT, so it's first order system. So at low frequencies, we have 20 dB a decade. And then at high frequencies, we flatten it out by putting an RL integration here. So we above 70 megahertz, it's flat or something. And below, we use math to reconstruct the waveform. It works pretty well. Now, this is with USB repeater IC. Here's the IC. And we have inputs for differential USB here. And there's voltage and current pickup here. And there's another pickup here. No, yeah, this is a current pickup. So basically, we have a bunch of USB repeater ICs, which we use for testing. We're testing soft failure, but also damage on to create models. And we have, this is an ESD generator. This is actually the circuit implementation of the model Bernd showed. It's just the circuit. There's a Mercury relay which switches. This is the ESD generator up to 2 kV. Here's a 1 ohm resistor to measure the current. And this is model and simulation, not a big surprise. I wouldn't show it if it's totally different. Then we have a transmission line pulsar. And here's a pulse, rises in like, I don't know, 200 pico. And this, it can go up to 2000 volt. And that's the, right now, this pulse length is 20 nano, but the pulse length can be adjusted. So basically the source models, ESD generator, TLP, they can be combined with, for example, with the TVS to characterize the TVS, or to make a system with TVS trace IC, or TVS common mode choke IC, etc. So this combination can be varied, and it's always the goal to create numerical models for each section, S parameter, SPICE models, combine them in simulation, and then check to measurement to verify that the simulation is okay. And if you verified enough simulations, at one point you gain trust. Yes, this is a modular system. I'm coming shortly to the end of my talk. We have about 60 models, launch modules, passive modules, RLC, common mode chokes, etc. A couple of active ones, USB repeater, some high frequency circuits for like cell phone stuff, CAN bus, and sources, TLP and ESD generator. And this is basically, basically to create models and to verify models for against simulation, because we're coming to the point where ESD protection cannot be designed by datasheet anymore. On really high speed I/O, one has to use other methods to design, and one has to refer back to simulation. And simulation is only good if one has models, and obtaining the models is a non-trivial task. And of course, the manufacturers are asked also to help to create the models. This is the point where I want to finish my talk, and I'm open to questions. Is the IV diagram mixed up in the first? In the first diagram, I was worried for a moment when I saw it. When I saw it, I had to think twice. If I and V access are wrongly noted, I cannot answer that now. But when I saw it myself, I was hesitating for a moment. So my answer is that this has to be. I have to look at it again. I hope that's a sufficient answer. Yeah. Then a similar question from Sebastian on another slide. I again need to check. I fixed some access notation, in the hours before the talk, but it doesn't mean I didn't make it worse. Okay, can a TVS handle a full ESD event? Yes. Many TVS, even with 0.1 picofarad IC discharge at 8 kilovolt, they can handle 30 amps peak current, and yes, many can. One has to just look at the data sheet, but there are devices with very low capacitance which can handle that. Okay, you mentioned a TLP. Can you explain more detail what that is? Yes, a TLP is the most simple thing you can think in the world. Think about, you take a coax cable. Let me grab a cable here. Grab a cable here, and you charge up the cable inside shield to the the shield to the inner conductor. And then you have another cable here, and you connect the inner conductor with a relay. Click, you close the relay, and this relay is closed in picosecond.
David,
Yes?
do you show something in the video, or because we still see
I
your
think my
presentation?
camera is on. Oh, my camera is off.
Ah, no.
So, okay, what I wanted to say, in TLP is the most simple thing in the world. Think about, you have a coax cable here, and the inner conductor, and this coax cable you charge up, so inner to shield, and there's another coax cable which connects to your 50 ohm system, and you connect them with a relay, and this relays, they switch in picosecond, 50 picosecond or something. Then the charge of this cable will go into here, and there's a 50 ohm system to 50 ohm, very nice, rise time fast, and so you can make a pulse which has double the length, double the electrical length of the cable you charge. That's called transmission line pulsar. It makes high voltage pulsars. Of course, you could start at 5 volt, you can go up to 2000, 5000 volt. Rise times, you can go down to 40, 50 picoseconds in a very well controlled design. Many have like 200 picoseconds. That's a transmission line pulsar. What's the range you define as high speed? Well, I mean, USB 2.0 I would not consider high speed, but anything where, let's say, the bandwidth is above, let's say, 1 gigahertz, but this, in 10 years, the definition would be different. But I say anything, if you need 1 gigahertz bandwidth, I would call it high speed. There are systems which run on 100 gigabit now, and that's certainly high speed. But 20 years ago, the definition of high speed was kind of different. It's a moving target. Do you have varistor models? Yes, we do have varistor models. For some of them, one can make more. Varistors are usually not that difficult to model, but we never intended for search testing. A very simple reason: our characterization system cannot characterize at the current levels which are needed for search. We would have to take a search generator. We have search generators, but this is sort of not the question we have been asked. In principle, it can be done, but it's something we have not approached. I think I got all questions.
David, there was one question left. If we can provide the LTSpice simulation model for the ESD gun. I think the simulation or the slides will be provided anyway. And in one of my slides, there was also the LTSpice simulation model, and also the values of the capacitors and resistors are on the slides. So if you just use the slide and copy it one by one, then you should also be able to reconstruct your LTSpice model.
Yeah, one thing I added to here as the answer is that the switch itself, one should set the R off of the switch to a very high value, like 1 giga ohm. I think the natural setting in LTSpice is 1 mega ohm for R off. That's too low. So that's the only thing which has to be changed from the native LTSpice model, I think. I don't know if that is in the circuit diagram.
In our simulation diagram, we still have a switch that is used in LTSpice, but you can also exchange the switch, which is a good way to do it, by a voltage source that will be triggered at a certain time. Because as David already mentioned, if you are using a switch in LTSpice, you have to define the on resistance and the off resistance. And even if the off resistance is in the giga ohm range, you have a voltage divider between the resistance of the switch and the impedance of your device on a test. And if you're charging up the capacitor to, for example, 15 kilovolt, then this 15 kilovolt will be divided by the giga ohm resistance of the switch and the input impedance of your device on a test, which means that already during the simulation, you will have a certain voltage at the tip of your ESD simulation. So the easiest way is to exchange the switch directly and use a kind of voltage source that is triggered at a certain time.
Yeah, IV is confused, by the way, isn't it? Yeah.
It should be voltage at the x-axis and current at the y-axis.
Yeah. This one is right, isn't it? This one is right. The other one is wrong.
This is a test for the audience if they are really taking.
Well, but it's also embarrassing for us. I mean, for you, no, for me. But okay, yeah, good for picking that up. I fixed the cup, and there were other errors. I fixed. Actually, I think that's one of the ones I fixed wrong. Okay. Any other question?
There's one question now comes. What type of ESD protection would you recommend to RF amplifiers?
Yeah, okay,
Problem
now
is
that's
often that they are sensitive to high voltages, but the output signal might be influenced by non-linear behavior of
yeah. That's a big story. We work quite a bit on this question of harmonic generation, and there are two classes of harmonic generation. One is by nonlinear devices like ESD protection. The other is metallic contacts. You know, they cause harmonics, like little clips or some connectors cause harmonics. We work on both, but if for an RF, let's say front end or an amplifier where you have to do protection, one has to be very careful what to do. I mean, there are many TBS diodes. They're made to produce not so many harmonics, but none are perfect. So in general, the best protection is a linear filter. So if let's say your signal is around 1.8 gigahertz, then of course you can make a bandpass filter, and then the bandpass filter will push away most of the ESD it comes. So that's like a ESD protection by a bandpass filter. But if you're broadband, then you cannot do that, because if your amplifier goes from 10 mega to 1 giga, you can put an inductor there to get a little bit rid of the low frequencies below, like a couple megahertz. But then you're faced with this protection problem, and then one has to very carefully look at the data sheets of which TBS devices to one side have can handle your power, but without causing too many harmonics. It's a very difficult design question, and all manufacturers of ESD protection devices are trying to improve their design to produce less harmonics. But it is a difficult question for certain situations.
Okay, so I think now we will stop with the presentation. First of all, thank you, Bernd and David, for this great presentation. It was really interesting, and now the questions, really nice. Thank you. If there are any questions left, we will answer them via email afterwards. So thank you all for your attention. I hope you enjoyed it. And yes, just let me show my screen to show you what's next. Tomorrow we start with a presentation with the title, Do You Know Your Component? Field Behavior of Different Passive Components. Hopefully see you there. It starts at 9, and yes, have a nice day.
Okay.
Thank you very much.
Thank you very much.
Bye-bye.
Goodbye.